Right, I'm really looking forward to the next topic at the innovation stage, because the company that the presenter stands for is a massive driver of innovation, and this is why he belongs here on the innovation stage. Topic is IoT-based energy monitoring for sustainable production, and I don't think I need to explain to you here in the audience how important energy consumption is in the present day and age. So we're creating a database for more efficiency, and you can see him here on my right-hand side, Claudio Geisert, Deputy Head of Department at Fraunhofer IPK. Enjoy the presentation. Thank you very much for this very nice introduction. My name is Claudio Geisert. I'm from the Fraunhofer IPK in Berlin, and I would like to present something on an IoT-enabled energy monitoring, how we did this at the IPK Institute. So just briefly on the agenda, I'd like to start with 2 slides on the Production Technology Center in Berlin. I will tell you a few reasons for increasing energy efficiency. Then I am going to present a very simple selection procedure for energy monitoring relevant production systems. Then introduce our energy monitoring system concept, and then give you an example for a central compressed air supply, because compressed air is an essential energy user in production. What you see here is our institute in Berlin at the Spreebogen, the Production Technology Center. We do research for the entire value-added chain, so from corporate management via virtual product development, manufacturing of products, and the automation of processes. Just a few facts and figures on our institute. The Institute for Machine Tools of Technical University of Berlin was founded in 1904. It's one of the, if not the oldest institute dealing with production technology as a science. The Fraunhofer Institute for Production Systems and Design Technology was founded in 1976 in Berlin. And then together in 1986, the Production Technology Center was founded. We have about 620 employees, fluctuates a little bit, an area of 9,500 square meters, and 90 test stands and special labs. And what we're very proud of is that over the course of the years, we have had 60 spin-offs that, for the most part, are still very successful on the market. Just a few words on our budget, an overall budget of 36.3 million euros, and the Fraunhofer Institute accounts for 24.2, and the other institute accounts for 12 million. So, a few reasons to increase energy efficiency. I suppose I don't really have to explain very much. We all know that climate change is very real. We can't get away from it. We have to take the right measures to handle it in some way or another, and in order to mitigate climate change as far as possible. And on the right-hand side, on the slide, you see that we have a strongly increasing electricity price. You see the development from 2000 to 2024, electricity price without taxes, the industrial electricity price. If you were to see this with taxes, then you would see a decrease. But here, too, it's quite clear that the levers of the federal government come to an end at some point, and we will have to live with the fact that the electricity price is going to go up even more, and this is going to be a challenge. Seeing to it that this electricity is generated in a green way. We all know the discussions about hydrogen hydrogen and other energy sources. And then we've got the measures that the EU has issued. There's the Paris Climate Accord, then there are the SDGs, the Sustainable Development Goals, then by 2045 at the latest, we want to be carbon neutral in Germany. Germany has set itself very ambitious goals here. And in production, things look rather different. Energy consumption in industry has increased by 4.6% in comparison to the previous year. And the distribution is, as you see here, 30% is accounted by industry. That's about the same share as for traffic and transportation. And then in mechanical machining, and we're at the EMO here, which is all about mechanical machining, the largest share of energy costs is accounted for by this. We've got pumps and compressors and the machine tools that you can see here, and they are, for the most part, powered by electrical energy. So this is one possibility. If you want to start off making your production more energy efficient, then of course there's always the problem of where to start and where to go. So you've got numerous instructions. We approached this in a very pragmatic way. We thought, well, what kind of influencing factors do we have? We've got the nominal power of the machines that we know from our data sheets. We know the different modes that our machines are operated in. So are they in stationary operation or are they highly dynamic? And examples for energy monitoring where it would make sense to do this energy monitoring are machine tools and compressed air compressors. Where you don't necessarily need direct energy monitoring is stationary pumps or conveyor belts or cooling units. Once they are stationary, you can really estimate quite well how high the energy consumption is just looking at the data sheets. And the more you monitor, the better the transparency, although, of course, you have to have a cost-benefit comparison. Now, how do you do this? How is the process? It's relatively easy. You look at the nominal power and see whether this has or goes beyond a certain relevant level. So, for instance, a bulb is not relevant. Machine tool with lots of kilowatt hours of nominal power would be relevant. If you have a static consumption, then you don't need direct energy monitoring, but can assess this via the switch-on, switch-off times. If you have a highly dynamic system, as you have it for most machine tools, then a direct electricity monitoring would be worth it. With energy monitoring, you can also do a condition monitoring of plants. We all know that a fridge that doesn't shut properly, where the seal doesn't work properly, uses up more power than a fridge that's working well. And the same holds true for the cooling units once the filters have been clogged up or pumps that don't work anymore. So our concept at the Institute was developed as a challenge, looking at individual production, plants and aggregates. So we wanted a modular, scalable system and a cost-efficient solution. And we wanted to have a solution that you can also use for energy management system according to ISO 50001. And also, we wanted to make it possible to have an order-related energy consumption billing. Order-related, this is important because you've probably all heard of the digital product passport, and the energy consumption per manufactured part is becoming more and more relevant. You could do this via life cycle assessment databases. However, usually this is an estimate, so it's much better if you have the direct energy consumption measured and can assign this to your product. So you can see our concept here on the right-hand side of the slide. It's not rocket science. You take so-called the transformers, current transformers that you use for the different phases of the three-phase network. Then you need an energy analyzer, that's the blue part right at the top, which is also enabled for ISO 50001 and provides the right parameters. Then you need an edge device in order to see to it that the data can be transferred to an IoT platform. And then you've got a dashboard where you can look at the individual parameters over time, and you've also got the results of the analysis. And here you see the basic architecture of the system once again. So as we see, there are three levels. The level of cyber-physical production systems of the plant itself, where our energy data analyzer is to be found, where we have the control of the machine. And these two provide data for the edge device. In case of the analyzer, Modbus is used as an interface, and for the PLC, you could do it traditionally via field bus, but that's a bit more cumbersome. So what's more modern is if you have an IoT communication protocol such as OPC UA and can look at the relevant data that can tell you something about the energy consumption. So in the edge device, the data can be pre-processed. If you don't have the raw data that you can transfer to the IoT platform, OPC UA comes in here, or MQTT. MQTT is the more lightweight protocol, which is very well suited for pure sensor data and transferring them into the cloud. This shows you an example for such a dashboard, such as we have it in the test hall. We've started in several projects to look at plants with direct energy monitoring. And I didn't say this before, we actually send out every single second the data, active power, reactive power, apparent power, but also the performance factor, which is the factor of how much of the apparent power is actually transferred into mechanical performance, which is what we want. So every second, these data are sent out for the analysis of dynamic processes. We also implemented hundreds of milliseconds. Only with us, due to our limited storage capacities, you can't do this all the time. In comparison with that, as a standard procedure, you usually do this every 50 minutes, send out data every 15 minutes. But if you have highly dynamic processes where you have performance peaks, it makes much more sense to really have a high resolution in terms of time and do it much more frequently. Down there in the dashboard, you see the pure raw data of the active power, and then at the top you see the evaluation. We can see on the one hand the consumption or the utilization of the machine. We can differentiate between a standby of the machine
operating mode, so when it is ready to work, and when is it actually working. And in order to classify this, on the one hand, there are guidelines by the VDMA, as far as I know, that tell us how this can be implemented via a threshold value. Now, this is suitable for series production, but we also have the opportunity of using machine learning procedures, the K-neighbors method, to have an automated cluster formation and to look at the 3 clusters that are relevant for me personally. So this gives you an overview of what your machine actually uses when it's in standby mode and how much it uses during productive work. It's no secret in many machining machine tools, most of the energy goes into the chips, but most of the energy is actually used to actually machine the bigger parts. So what are the advantages, and what does all this have to do with sustainability? Well, we create a high degree of transparency for electricity consumption, and once you see this with your own eyes, then you really are amazed about where all the energy goes in your company. You also know that many machines aren't switched off at all. Never change a running system. Everybody always says, and who knows whether the machine will ramp up once again. And in production processes, you sometimes have very long heat-up times which prevent industry from just switching off machines. There are some control manufacturers that provide methods that ensure that a machine can have its heat-up phase before the shift starts. So there are many ways of using standby modes, and the big question when it comes to cooling units is, do they really have to run all the time, or can they also be switched off now and then, because they really contribute a lot to the energy consumption of a plant? We calculated there's such a plant which in operation has 2 to 2.5 kW of consumption. If you look at the non-productive times, so if you go on the basis of 2-shift operation, if these machines aren't switched off, the consumption is more than a household with 2 people would use in the entire year. So this is really an appeal to the industry. Low energy prices, of course, not an incentive to use as little energy as possible. But if you combine both things, then your production can become much more efficient. So at the end of the day, if you do this kind of energy monitoring, you can look at potential savings of energy, and when it comes to energy consumption, this is also a KPI for production, which becomes more and more relevant in the present day and age. Now, this is my example. I hope you can see it well enough. We chose an example where we wanted to find out in an automated way when a machine is in operating mode and when it's in the standby mode, and we took notes on when the machine or the machine operators jotted down when the machine was ramped up, when the orders were machined, and you see here quite clearly this is not a series production. We're a research institution, so we have longer breaks in between and alternating orders. So we automatically analyzed how many watt hours a process took, and you see the same process took about 2.7 or used up 2.7 kilowatt hours on average, and in standby mode, which is depicted in green, shows you that 650 watt-hours were consumed. We did a clustering, a classification. You could do it with as many categories as you want. You can always do, this type of clustering. You can define the categories, or if you don't know how many categories of operational modes there are, then there are machine learning processes to solve that problem for you. And there are also requirements, and we took standby, operative, and unknown, as we called it here. And in this particular case, it was random forest. It was the random forest classifier. And as you see, by the 3 different colors, we could identify the 3 different modes very simply here. So if you want to ask about the quality of categorization, this was just an example. We know that we're talking about machine learning. The more data you have, the better the algorithm will perform. In the end, we didn't have that many data, so we can assume that the quality of categorization isn't necessarily usable for many other processes too. It's not representative. Another example in the area of compressed air supply. So we assume that we have a compressor which has an air tank, which fills an air tank, a compressed air tank, and usually it has the behavioral pattern as you see it up here on the slide. So you have a 2-point controller. There's a lower pressure where the compressor switches itself on. Then it runs with a permanent performance until the upper pressure is reached, and it goes on in this way in a kind of zigzag fashion. So the pressure always goes up and down a little bit within a certain range. This is a constant pressure consumption, and in our hall it looks as like the image shows you at the bottom. You can see the active power here, and what you see very clearly is that the times at which the compressor is off are shorter than when the tank is being filled, which leads to the conclusion that we have rather high leakage values. What's also interesting is that the energy costs account for 80% of the service cycle of a compressor. So such a compressor has energy costs. The purchasing costs are more or less negligible. And from literature, we know that in industry leakage rates are between 15% and 50%. There are methods to ensure that leakages can be located via microphones, but all this is very cumbersome, and an easy method is actually looking at the switch-on, switch-off behavior. There's also a rule for this and a formula for this, on the basis of which this can be calculated, which is what you can see here. I don't want to go into this in more detail, though. However, it's important to know that the switch-on, switch-off times are counted. Then you have the flow rates of the compressor as it is set from the data sheet, and then you can look at the leakage rate and calculate this yourself. And up here you see that with the help of a machine learning, the k-means clustering in this particular case was able to calculate the standby and operative times, and this means that the blue areas are the areas that we can use to determine the leakage rates. Right, and to wrap up, in order to produce sustainably, energy consumption and energy monitoring of consumption is the foundation if you want to use any levers in a positive sense. So energy consumption monitoring is a positive thing on the one hand to make production more energy efficient, but it can also be used for condition monitoring, for predictive maintenance, and all in all it's also good to reduce energy consumption as a whole. The creation of transparency in energy consumption in production is really the first step that you need to take before starting to use any other levers, more or less without any real agenda. So it's really good to look at all this before you do anything else. It's not rocket science, as I said before. Energy monitoring can be installed rather simply, also on an IoT basis, without manual notes or anything like that. And our offer to industry is that we can analyze your energy consumption with the steps that I outlined before. We can accompany you and consult you and support you when taking the energy data, and we can also consult you on appropriate energy efficiency measures. And they could be of an organizational nature, but they could also be of a technological nature. Processes could be optimized. We have a process for plastic printing where we showed how much optimization potential is in the different process steps. And then the question always is, where is it worth it? Where isn't it worth it? What's the payback time? And of course, we would also support you if you have an ISO, if you need an ISO 50001 certification. The work that we did was supported by the Regional Transformation Network for Berlin-Brandenburg in part, and this project has the aim of ensuring that the automotive industry can be supported in its transformation in the direction of electrification. And at our institute, we set up a real live lab that I would like to invite you to, where there we've got different scenarios that we can present, from 3D printing, AI assistance for production and maintenance, but also for energy monitoring, of course, but also working with collaborative robots. So you can see all that in our lab. Right, and this brings me to the end of my presentation. Thank you very much for your attention. Please see us in Hall 14, booth F15, on the sustainability booth of the WPG, and I'm happy to take your questions. Yeah, we don't really have that much time left for questions because the presentation was so good. But I've got one question. What's the next step? Are you talking to partner companies when it comes to introduction? Is that the current status, or what is it actually? Answer, well, the current status is that for many companies, this type of energy monitoring that would be possible on the basis of IoT has not been implemented. So the next step would be not only capturing data and making it transparency, but look at peak improvement and intelligent evaluation, trying to reduce energy consumption. By the way, an appeal to all machine tool manufacturers. As far as I know, energy monitoring in the machine tool is not a standard option, but it's got to be asked for specifically, you're shaking your head, but I suppose that it's more than 50% of machine tool manufacturers that don't offer this as a default. Thank you so much for your presentation, for the topic. Thank you very much once again.